didn't. So it's not good recording. Okay. All right, on this happy note, let's continue with the most thrilling topic. Okay, so let's do recap questions. Without looking at your notes, what's the difference between electronic and vibrational energy, and to what spectral region each corresponds to? Everybody, don't look at your notes. Okay. Smiles. Maddie is smiling. No? Sophie?
So electronic refers to the electrons and which level they're on.
Yeah. Yeah.
And then vibration is how bonds vibrate within a larger molecule.
Yes.
So electronic is UV bits.
Yes.
And vibrational is IR.
Yes. Sophie, great. Probably you deserve a +4 on this. 2 participation. No, this is great. So electronic energy is basically, by the name, what the name implies is when an electron in the valence shell gets excited and moves on to a higher level, once absorbing the photon of light. And this would be in the spectral region of UV and visible range. Whereas vibration, again from the name, is the vibration of bonds, stretching and bending of bonds. And this corresponds to spectral region of IR. Okay? So atoms can absorb electronic energy. However, there are no bonds when you have free atoms, so they don't have vibrational energy. Whereas a molecule can have both electronic energy, vibrational energy, rotational energy, rotation around the center of the molecule, but that is not relevant for the analysis. Okay, so what's the difference between absorption and fluorescence spectroscopy? What the name is telling you. What's absorption? Yes, Sammy? Exactly. So absorption spectroscopy has to do with measuring absorption of light. Fluorescence has to do with measuring an emission of light. And emission of light usually happens at a longer wavelength. So because some of the energy is dissipated as heat, so the emission would be emission of a longer wavelength energy, and the energy will be of lesser energy than the absorbed energy. Okay, what's the difference between diffraction and refraction of light? What's the diffraction of light and the refraction of light? Brigitte?
Diffraction. Sorry.
Yes?
I just went with something else.
So you know refraction then?
Yeah, refraction is when light came through, but then it didn't reflect, and it just kind of bent.
Yeah, change the angle at which it hit a different medium. So diffraction is when the light enters from one medium to the other medium and changes the angle of the travel of that wavelength, or the wave of light. Okay, so diffraction, this is in a monochromator, for example, when light gets onto a prism or a grating system, and then it diffracts into multiple waves of particular wavelengths. So instead of all of the wavelength hitting a sample, it gets into a monochromator where the lights diffract into wavelength of individual waves, of individual wavelengths. How does the wavelength impact the frequency and energy? So longer wavelength versus shorter wavelength. So when you have a wave with long wavelength, does it carry more energy? Does it have higher frequency, or what? Paul?
So longer wavelength will have lower energy and lower frequency.
Exactly. So, and the wavelength is basically the length between two optimum within an optimum. to recurring oscillation. They do get it. Since they showed up, they'll get the plus 10. You were about to lose it. Okay. What is Beer's law? Well, with excitement. You will sing it, yeah.
Beer's law is the equation that deals with the linear relationship between absorbency and concentration.
Yes! What's that? He gets plus 3 on this. Yes, I'm not going to sing it for you, but it's correct. It's the relationship between absorption and concentration, and it's a linear relationship. Perfect. Why absorbed light is not equal incident beam minus transmitted light. So what's incident beam? So the light hitting the sample versus the light that leaves that compartment of the sample, so the transmitted light. So why it's not a simple subtraction? So the absorption is not a simple subtraction from what hits the sample versus what leaves the sample. Okay, so that's okay. We don't remember that one. So it is not that way because some light gets reflected, some light gets scattered. So it's not necessarily whatever is not transmitted, that means it got absorbed. Okay, good. We're all back on track. Jason. Hi. So Jason, I gave plus 10 to whoever is in the room.
Oh, so is that like
You're,
one for me?
yeah, so you still get it.
Like 4 points?
Plus 8. Okay. It is essential to accurately measure the fraction of light that is absorbed. So basically what we do is we have our sample in a matrix. So the carrying matrix, the solvent that it's in, the medium that the sample is in, that medium may have components that also absorb light at the same wavelength. It might have components that scatters light. It might have, and then you have the reflection of the light that hits the cuvette where the sample is. So we always have a blank. So our blank can be water if our components are dissolved in water, but it can also be the same reagents you use to have your sample in to be measured. So your blank is everything but your sample, but the components of the sample. So you put that solution of the blank in your cuvette, and then you run it in your spectrophotometer, and you subtract that absorption from your sample. We call this term zeroing. And some of you that did the AA kind of did that already by running a blank. So what you did is you took an empty crucible. Those of you that did the lab, those that didn't do the lab will do it next week. And you put in all of the reagents and run it through the entire dilution scheme and preparation that you did for your actual sample, and ran that on the photonic absorption and use that to subtract the value of the blank from the value of your sample. Okay. Beer's law and deviation from Beer's law. In order for the Beer's law to work or to be reliable and accurate, we have to make sure that certain things are not causing deviation. So for example, the concentration of your analyte. If you have a high concentration, your components, the molecules, are going to be in close proximity to each other, so they would impact the absorptivity. So you really don't want to analyze at high concentration. So you want to always dilute your sample. Also, dilute the sample in a way that you have linear relationship. So that's why, depending on the component you're analyzing, you have different range of concentrations for your standards. Some have to be lower than others in order to maintain that linear relationship where you don't have interference due to intermolecular interactions. Chemical processes. So what would be the pH in the system, for example, that might cause dissociation or association of the molecule, losing a proton, gaining a proton, getting ionized. So that impacts the ionization and association, dissociation, again, impacts absorptivity of your molecule. So you want to make sure that your system is not impacting the chemical nature of your molecule. Polychromatic light, I think we touched upon that last time, is you don't, polychromatic, that means light that consists of waves of varying wavelengths. So when you're doing a concentration, you are looking at measuring your concentration, you want to make sure that you have a narrow band of a monochromatic light. That means you have one absorptivity. If you have multiple wavelengths of different wavelengths, you have multiple absorptivity, and the equation only have one absorptivity, the Bier's law. So whenever we're calculating concentration, we have to select the wavelength and have that absorptivity used in that relationship. Okay, other consideration for procedure. Sample preparation. So when you prepare the sample, your sample needs to be homogeneous. So you don't want a dispersion. You want to have a complete solubilization, like a solution that is homogeneous. Also, you want your solution to be clear. Oftentimes, we don't have a clear matrix. What we do is we centrifuge and take the supernatant and then measure absorption. Because you don't want particulate in your sample. The particulate are going to scatter light. So homogenization and clarification. Reference cell and appropriate control. So some spectrophotometers have a reference cell where you have your blank in it, and always your light is split into the reference cell and your sample cell, and at the end gives you an absorption that is already corrected. Some spectrophotometers don't have that. You have to manually put your blank and measure it, and either zero or subtract later on. And it's important to put that multiple times. If you have many samples, let's say 50 samples, it's important to put that blank or a fresh blank every like 5 or 10 samples, so that you maintain the zeroing. Otherwise, you will have deviation over time of measuring. Chemical modification, correct modifying reagents, correct for modifying agent. That means that's the use of blank and using the same reagents except for the sample. The other consideration is the cuvette that you'll be using. So there are different types. Quartz and fused silica, these are types that do not absorb UV light. So when you're measuring absorption in the UV spectrum, you want to make sure it's not glass or plastic that you're using, because glass and plastic can absorb UV light. So, however, visible light, you can use glass cuvettes or plastic cuvettes. They don't interfere with the absorption. The other thing is the amount of sample. So the length of the cuvette usually is about 45 millimeters. That's kind of a half centimeter. That seems small to me, right? Isn't it like this big, like an inch? Yeah. Why does it say 45 here? That doesn't seem right. That's too small of a cuvette. So usually your cuvette is about 5 centimeters long, and when you put it in your spectrophotometer, there's the path of light. You want to make sure that you have enough sample in it so that the light is passing through it where the sample is. If you have very little sample, the light will be passing on top of it, so that's not good. But sometimes you have sample limitation. You don't have enough sample. So there are unique cuvettes that have dimensions that allows you to put your small amount of sample and still have the desired height where the light can actually go through the sample, not just above the sample. So, other procedural consideration is obviously selecting the optimum wavelength. And you remember that from the HPLC lab, we selected 272 nanometer for caffeine. We selected the lambda max. If you remember what that is, what is lambda max? You guys wrote the report, didn't you, already? You all have had it in your abstract, didn't you?
So the wavelength that is
What?
lambda mean right in which we measure.
It's the wavelength at which we measure.
Well, that's the light wavelength.
It's a light wavelength. Yeah, so maximum what? Yes, maximum absorption. Lambda max is the wavelength at which we get maximum absorption. Your molecule absorbs light at multiple wavelengths, but it has a wavelength at which you get maximum absorption. So that's when you have the highest sensitivity. So sensitivity is the ability to detect small differences between in concentrations among samples. So when you select that wavelength at or lambda max, then you are maximizing sensitivity. And then usually it has to be so narrow, the bandwidth, that you can control actually in your instrument. You can control the bandwidth or with the opening that allows the light to go, the wavelength to go in. The narrower it is, the narrower the range of wavelengths that can go through. And then the more sensitivity you get with the maximum absorption. And of course, you have greater adherence to Boo's law. When you have that narrow band with the narrow range of wavelengths, hopefully within 1 or 2 nanometers, then you can get that maximum adherence to Boo's law. We often calibrate the instrument in such a way that we calibrate it to read zero transmittance, where we cover the light so that no light is going through, and we say this is zero transmittance. And then without having a sample or a blank or anything in there, or no covettes at all, so we open that light and allow the light to pass through to the detector, and we say this is 100 transmittance. So we calibrate the instrument, then we put our blank and we zero. Okay. Another important thing, very important thing, is that if we want to obey Boo's law, the relationship between absorption and concentration has to be linear. So when we build our standard curves, we have to make sure we use concentrations where we have linear relationship. Closest to R squared of 1 that Cindy got with the AA. Usually I tell students, nobody gets an R squared of 1. There is no perfectness in life. Yet Cindy got R squared of 1. Okay. What's that? It rounded it. But it was very, very good. Very good linear relationship. So every element or every molecule have a certain set of concentration where the relationship is linear. Beyond that concentration, it might plateau, so you lose linearity. So when you prepare your sample, you do not want to prepare a concentration where you don't have that linear relationship. When it comes here, you're not accurately determining the concentration anymore. So we always, when we select our standard concentration, we run it to see if we get linear relationship. And then we establish, okay, linear relationship is between 0 to 10 millimolar for that particular compound. It seems like here it's 0 to 5 for this other analyte. But for this particular compound, it's 0 to 10. So I want to make sure that my concentration of your sample is approximately in this range. Sometimes you don't know. You just randomly dilute, run your sample. Nope, it's not in the linear range. You go back, dilute it again until it is in your linear range. Okay, life gets complicated. And sometimes your sample is present in a matrix that has a lot of interfering substances that will impact your absorption. And then when you come to prepare your standards are prepared in nice solutions, don't have the complexity of your sample matrix. Now, can we relate? We cannot relate. So your standard is in a matrix that doesn't have interference, and then your sample is in a matrix that has interferences with other compounds. So what do you do in this case to calibrate? We call what it is an addition protocol or standard addition protocol. You may encounter this later in life where you are a scientist in a lab and you want to calibrate and you're hit with a sample that is very complex. Then you might need to use that method to calibrate. So let me visually draw a schematic here. So the way you would do that is you build a standard curve with your sample matrix. So you have your sample matrix, and then you get nicely shaped volumetric flask. Okay, 4 to 5 would be good to build a standard curve. And then you put the same amount of your unknown solution in here. Same volume. Volume of unknown solution would be the same. And then now you have a stock solution of your standard. Okay, so now I want to build a concentration gradient of my standard within my sample. So I put a different volume of the standard in each one of those. So now I'm building my gradient or my different concentration. And then after that, I make up to the same volume, whatever it is, 10 milliliter, 50 milliliter, 100 milliliter, whatever is my volume. So after that, now I have my sample is in there, and I'm after calculating the concentration of my sample. I don't know that. But I know the volume in each sample, and with that, I know the concentration within each sample, the volume of each standard, and then the concentration of each standard in all of these. Then I measure absorption, and I plot it over the volume of the standard. Okay. Volume 1, 2, 3, 4, whatever the volume I'm using. Then I get the equation of the line. The equation of the line has a constant, so there's the absorption. The constant is your path, the path of the light, so that means the width of your cuvette. What's your cuvette in AA? Those of you that got done the AA. Did Cindy tell you? Yeah. So those of you that did AA, what is the cuvette in AA?
It was the best part.
Huh?
It was the best part.
It was the best part. Should we give -2? Who did AA? Raise your hand. He's the bravest soul that admitted that did the AA.
I don't remember.
Half of you, 20 of you did the AA. Who did the AA?
So the cuvette is also
Huh?
sample compartment.
What's that?
We can call it the sample compartment.
Okay, so the sample compartment in AA. What is the sample compartment in AA?
Yeah, he said it.
John,
There's the flavor.
what's the flame? Yes, the flame itself. That's where the sample is.
not made out of plastic.
Ben -2 to all AA. He was happy. It's fine. Okay. So then back to this. K is the path length of your cuvette or sample compartment multiplied by the absorptivity. So this is a constant. And then all of these here, you know it. So you get your absorption from reading the absorption. You have the volume of the standard. You have the concentration of the standard. You have the volume of the unknown. You don't have the concentration unknown. That's what you're searching for. You have the volume total, whatever is in your total volume that you made up the volume. And then, voila, you have the concentration of your sample. Okay. We're good? What's that? Yeah, last time. Yep. Okay. Indiscriminant error associated with absorption or absorbance transmittance measurement. What is indiscriminant error? We call this instrument noise. When you get the signal for no reason, when you get the signal that could be due to interfering substances in the sample or due to carry-on contamination. So these are noise, we call it, not the real absorption. So which one is this? A. So wait, let me read the others. Has to be small relative to variation from sample prep sampling the agent handling. So your sample, your noise should not be similar to your signal from your sample. If that's the case, then your sample is too dilute. So we will have to go back and concentrate the sample so there is a really good difference between the instrument noise and your sample, the signal. Can be tested with repeated measurements of a single homogeneous sample. Yes, that is correct. So every time you run the same sample, you're going to see the same signals coming up. Can be reduced by use of intermediate concentration. That is correct. Too high of a concentration is not recommended. Too low of a concentration is not recommended. Sometimes they tell you the best is to have an absorption between 0.2 and 0.8. That would give you the least signal to sample ratio, or not signal, sorry, noise to actual sample signal ratio. It depends though. Sometimes an absorption of 1 and 1.2, it's still good. You just have to determine which is the best absorption and which is the best concentration for your sample. But rule of thumb is you want to have an absorption between 0.2 and 0.8. Okay. Instrumentation. A lot of the spectrophotometric units, they have a monochromator. A lot of them do. So you have your lamp, the light source. In UV, it could be deuterium. In visible light, it could be tungsten. So you have your source of light, and then you have all of the light gets onto your monochromator. And then a singular wavelength comes out of the monochromator that you selected. So this is what it is. So the light goes in, and due to the geometry of the instrument, you often have mirrors that contain everything in a small compartment. So the light goes in and gets reflected by the mirror onto a grading system. We call it diffraction grading, or sometimes we have a prism. And then the light then gets diffracted into multiple light wavelength, and then a certain wavelength is allowed to get through the entrance of light towards your sample. So the sample will be here. So it goes, what am I saying? No, scratch all of that. Okay, so this is the entrance of light, and then it hits the grating, and then it gets diffracted into multiple wavelengths. All right, so now you have your light diffracted into multiple wavelengths, and the exit slit that gets onto your sample is programmed through the instrument to allow a certain wavelength of your selection to go through. Okay, so all of the light hits the mirror, gets onto a diffraction grating system, gets into a mirror again, and it's diffracted, and then the selected wavelength exits and hits your sample. So now you have a monochromatic light that enters your sample, and the sample components that absorb at that wavelength absorb light, and then transmitted light makes it to the detector, and then the detector converts the signal of light into electrical signal and gives you absorption value. So we have two types of detectors that I'm going to talk about. This phototube detector. This is a phototube detector. So in this detector, what happens is when the light hits, the beam of light hits a cathode, the cathode emits an electron, and the electron is withdrawn towards an anode, and the anode then now the electric signal travels through the anode, and you get that signal of absorption. Okay, so the light is converted to electrical signal. So you have, this is a singular phototube design, and you have a photomultiplier design. So the photomultiplier is to enhance the signal, to enhance the threshold of your detection. So the same beam of light will hit your first cathode. Here an electron gets emitted, and it hits a diode and emits more electrons, and then another diode, and another, and then the one electron becomes 27 electrons that gets picked up by the anode, and then your signal multiplies. So you enhance your threshold, you enhance your sensitivity. This is the type of detector that you have in the atomic absorption detector. So the detector that you use, or half of you already use, is the photomultiplier detector. The photodiode detector, or we call it photodiode array detector, and we talked about it in the HPLC lab. In this case, you don't have a monochromator. What happens is that all of the light hits your sample, and the components within the sample absorb light at multiple wavelengths. Then you get the spectra. Show you the absorption at multiple wavelengths. After being absorbed, after absorption occurs, transmitted light hits an array of photodiodes. Multiple photodiodes. We call them photodiodes. They convert photons of light into electrical signal. So each photon of light of a different wavelength will be converted to an electrical signal. So we get all of these different electrical signals due to different wavelengths hitting the detector, generating the absorption spectrum. And hence, we can read absorption at multiple wavelengths, scan at multiple wavelengths. Yet, if we want to quantify, we have absorption at multiple wavelengths. We select the maximum absorption, and we get that and plot it against concentration. So we get two benefits of the photodiode. One benefit is the screen, the fingerprint of identification, and on top of that, we can select whatever wavelength we want to quantify and apply Beer's law. So we select the 313 in this case, plot the area at that wavelength, and then get our concentration that way. Area or absorption, sorry, depending on what method you're using. So the design of the instrument, you have single beam and double beam. So the single beam, you have one cuvette, and then all of the light gets onto that one cuvette, whether you have your blank first and then your sample, so the light gets directed to that one cuvette. And it can, if you have a monochromator, it will diffract the light, and one wavelength gets the sample, and then gets to the detector, and then convert it to a signal. You can have a double beam, so that means in your setup, you have two cells, one for sample and one for reference. The source gives you the light, and the light gets split, and part of the light goes into the sample and part of the light goes into the reference, and then you get transmission from both, and both entering the detector, and then you get automatic correction of absorption. So the absorption gets corrected by subtracting the reference absorption, and then you get one reading. So here you don't have to measure the absorption of a blank individually and manually subtract. Here the instrument does that for you, and then the reference remains there. So every time your sample is measuring absorption, you are already correcting for that. If you don't have that reference cell, you have to, like I said earlier, every few sets of sample put a blank and zero again. Here you don't need to do that. It's automatically zeroing for you every time you measure the absorption of your sample. The only downside of it is the radiant power is diminished. That means because the light is split, so you have less power going through. That is the only kind of disadvantage. This is just FYI kind of table to show you different groups and how different groups absorb, have different absorptivity. And different lambda max. So, for example, acetaldehyde will have a lambda max at 290 and have a molar absorptivity of 70. So, a lot of the different groups, you can find absorptivity value for them because they've been determined, and the lambda max has been determined in literature. So, depending on what you're measuring and what you have in your as functional group, you can go and determine what would be an absorptivity. If you know the absorptivity, you don't have to have a standard curve actually. So if you know the absorptivity is absorption equal absorptivity times the length of the path of light and multiplied by concentration. So if you have the absorptivity, you don't have to have a standard curve. Fluorescence spectroscopy, the setup is pretty much the same with one additional component. So in fluorescence spectroscopy, we're not measuring absorption, we are measuring emission of light, the fluorescence. But we have to have a selected wavelength for absorption. So you have to select the absorption wavelength, and then you have to select the fluorescence wavelength. So that's why the instrument has two wavelength selectors. So you have your source of light, you get to the wavelength isolator or monochromator, and then you get your incident beam at the selected wavelength, and here's your sample. It absorbs light, and then there's light transmitted, but the geometry of the instrument allow a 90 degrees fluorescence light to go towards the detector. So the emitted light is projected at a 90 degrees angle, and it goes through a monochromator again, where you select the maximum or the wavelength at which you have maximum fluorescence. Then you filter that out, and then it gets to the detector, and then you get a readout. So that is the difference. You have two wavelength isolators or monochromators, here, and then the angle is projected at a 90 degrees. So you have to select wavelength here, and you have to select wavelength here. Excitation and emission. So we have excitation wavelength and emission wavelength, and remember the emission wavelength has a longer wavelength because it carries lower energy. Okay, great. Guess what? You have 5 more minutes. Should I send you home? No? Don't do it? Alex, do it? Huh?
Okay, we'll sing again.
Okay, go home. Have a great weekend.
Okay, so I have this, right? It has like my stuff.
That was on Anjula. I don't think she was here.
I didn't see her.
Okay.
Usually she sits next to Hiju.
Yes, I'm
Hiju is
You
the...
know, like,
not Hiju, I mean Chenyu.
Okay.
He usually sits next to him, and he was there. If you don't see anybody next to him,
Okay.
I can't tell for 100%. I always feel
yeah, no, I need a person.
I need a little...
Okay, for sure.
Yeah.
Alright, have a
That
good
would make
weekend.
sense because it counted.
Yeah,
I saw you taking away.
Okay.
Yeah.
you don't have to, I just thought with teaching you that
No, okay.
thing that like,
It will
you know, like,
Okay. So
What are you? Okay, so I don't know. Oh, okay. So food analysis has its own folder.
And one was orientation.
Yeah, so he's auditing all of this stuff.
Oh.
This is
Just within the food analysis lab. So okay, that's what that is.
Cool. Do you want this back or?
Oh.